In this video, we are looking at the theory of RLC circuits. The first question, define capacitive reactance with reference to RLC circuits. Is the opposition to the flow of current when a capacitor is connected to an AC supply. VL lags IL by 90 degrees. Question 2. Define inductive reactance with reference to RLC circuits. Is the opposition to the flow of current when an inductor is connected to an AC supply. IL lags VL by 90 degrees. State the phase relationship between the current and voltage in a pure inductive AC circuit. Lagging. Define the term bandwidth with reference to RLC circuits. Bandwidth is the range of frequencies for which the circuit output voltage or current value equals to 70,7% or more of its maximum amplitude, the small band of frequencies centered around the resonant frequency. Define Q factor of an inductor in a resonance circuit. Q stands for quality factor of an inductor, refers to the ratio of the inductor's reactance to its internal resistance during resonance. Define the term impedance with reference to RLC circuits. Is the total opposition to current flow to an AC circuit comprising of resistance and reactance. Define the term phase angle with reference to RLC circuits. Is the shift in phase between supply voltage and the circuit current, which results from complex circuits with reactances and resistances. State the relationship between inductive reactance and frequency. Directly proportional to each other. Describe what is meant by in phase with reference to the relationship between the applied voltage and the current in an RLC circuit connected to an AC supply. When the voltage and current waveforms start at the same time, have the same frequency, resulting in a zero phase angle. Name two applications of resonance as applicable to tuned circuits. Radio tuning circuits and television tuning circuits. Define power factor with reference to RLC circuits. Is the ratio of true power to apparent power. Define the term Phasor diagram with reference to RLC circuits. A phasor diagram is a graphical representation of a sinus graph alternating current or voltage in an RLC circuit. State the phase relationship between current and voltage. So, in this diagram, state the phase relationship between current and voltage. This would be an inductive circuit because IL lags VL by 90 degrees. So if we come to the graph, we will notice that the V is starting at 0. So the V starts at 0 degrees. Notice that I is starting at 90. So comparing this point and this point where they're both in phase, where it looks like they're in phase with each other but they're not, notice that it starts there and it starts there, but they have the exact same pattern, right? If this point was in phase with this point, this means that this graph here, this point here, would be there, and then they'll be totally in phase with each other. So this means they are 90 degrees out of phase. The current lags the voltage by 90 degrees because it's starting 90 degrees later. Draw the phasor diagram that represents the AC waveform below. So this question is saying look at the diagram and draw the vector diagram or the phasor diagram for the lagging or leading. Use the same explanation as I did before. Notice that VL leads IL by 90 degrees. Coming back there, notice this point here and notice this point here. Notice they have the same shape. If this point was exactly on that point, they would be in phase. So notice that the current is 90 degrees behind the voltage. So this would be the phasor diagram. Also include the direction of rotation, which is always anti-clockwise, and include the labels. Identify the graphs below. So looking at the graphs, notice that the axes have no labels. So knowing the curves, one would have to consider what it is. So A, this is graph A, is the impedance versus the frequency. So there's frequency, this is impedance. Graph B, notice we have the frequency and we have the current. So graph B is the current versus frequency. Coming back to the graph on the left, we'd have to think what is going on there. This would be a parallel RLC circuit because the impedance is at a maximum. So if the impedance is at a maximum, this means that the current is at a minimum in a parallel RLC circuit. So parallel RLC, impedance is maximum. This means the current would be minimum because they're inversely proportional. Consider the graph on the right hand side, graph B. Notice that graph B would be a series RLC circuit where the impedance is minimum. So if the impedance is minimum, this would mean that the current is maximum. State two factors that affects power dissipation in an AC load. The magnitude of voltage and current the phase angle between the voltage and the current. Draw the phasor diagram for the waveform below. So again, you have to draw the vector diagram or the phasor diagram for that graph below. Notice that they are in phase, and because they're in phase, they'll be exactly in a straight line. Notice that VR is greater, so this is why VR is greater than the I value. Notice that the I only goes up to that height, so it is a shorter distance than VR. Draw the phasor diagram for the waveform below. So there's our waveform. Apply the same concept to draw the vector diagram or phasor diagram. Notice here that if we were to look at the I, that is the I value, notice that I, and this is a V. So let's look at this point and this point. Notice that there is 90 degrees between it, and which one is greater? I. So I is first. Do you see it? So I is 90 and V is 180. So it's 90 degrees later. So notice there's a 90 degree angle. The current is leading the voltage by 90 degrees. So looking at the rotation, which is always anti-clockwise, the current is then leading the voltage. State the phase relationship between current and voltage in a pure inductive AC circuit. There is a 90 degrees phase shift between VL and IL, where IL lags VL by 90 degrees. So in an inductive circuit, a pure inductive circuit, the current lags the voltage by 90 degrees. Define the term pure inductance. A pure inductor is one which has no resistance, no capacitance between its ends. Explain the effect Lenz law has on an inductor in an RLC circuit connected across an alternating supply voltage. It will affect the phase angle. It will oppose the current flow in a circuit. Lenz law states when AC flows through an inductor, a back EMF is set up, which is opposite to the applied voltage. A circuit is almost at resonance. Then after decreasing the frequency, the current increased slightly. Explain why this happens. A decrease in frequency caused the inductive reactance to decrease and the capacitive reactance to increase. When these two values move closer to each other, the effects cancel each other out. Decreasing the impedance causes the current to increase and the phase angle to decrease. State two characteristics of a parallel RLC circuit. Z is maximum, I is minimum, XL is equal to XC. Define the term resonance. Resonance is found at one particular frequency. The inductive reactance of a coil will be equal and opposite to the capacitive reactance. At this point, they are exactly equal and cancel each other's effect. Explain why the phase angle is 0 at resonance. Because XL is equal to XC and thus VL is equal to IL, R is equal to Z. State 3 conditions that will occur if the power factor is at unity in an RLC circuit. So XL is equal to XC, IL is equal to VL, R is equal to Z, current is maximum, impedance at minimum, the phase angle is equal to 0. This is for unity power factor. So this means that cos theta is equal to 1 and cos of 0 degrees is equal to 1. Describe the difference between the characteristics of series and parallel resonance. Series, current is maximum, and in parallel, current is 0. Series, impedance is minimum, and in parallel, impedance is maximum.